So let's summarize the equations that we've developed so far for the bending beam. So we have a lot more than we have for the other simple cases of axial forces or torsional forces on beams. We have three equilibrium equations, first of all. So those are the sum of the forces in the vertical direction, sum of the moments about the z-axis, and sum of the forces in the x direction. For each one of these internal resultants, m, v, and r, we have connections between them and the stresses on the cross sections. So we have these integrals, or the cross-sectional areas, of the bending stress times the lever arm gives us the moment, the integral of the shear stress gives us the shear force, and the integral of the bending stress without any lever arms gives us the axial force. We have three kinematic relationships. There's the fundamental one, which we got from plane sections remain plane and normals remain normal, which says that the bending strain is equal to minus y kappa. So if you want, you can write that as epsilon xx, just to be very specific. So bending or normal strain in the x direction. Then we have curvature. If you want to be precise, curvature about the z-axis is the derivative of the rotation of the cross sections with respect to x, and the rotations are connected to the deflections of the beam through one derivative with respect to x. So this is all small strain, small motion assumptions here. So these are the equations that we've developed so far. If we count them, there are 9 equations in total. The unknowns are the three resultants, m, v, and r. There are 2 stresses, the bending stress and the shear stress. There is the bending strain, the curvature, the rotation, and the deflection. Plus also, there's the location of the center of rotation or the neutral axis. So remember, in all of this, we placed our coordinate system at the location of the center of rotations. That's how we were able to write down our fundamental kinematic relationship here. And so that's also unknown. We have to figure out where the origin of the coordinate system goes in all of these. So in some of the examples, I just stated where it was, but in principle, you have to determine that before solving any problem. So there are quite a number of things to be treated in beam bending problems. Now, if I count the number of unknowns here, I'm going to find out that I have 10 of them, and I have 9 equations, so there's one missing equation, and that missing equation is the same one that we had before when we counted up our equilibrium and kinematic relationships. The way we closed this system of equations was to introduce a constitutive law, so a relationship between the stresses and the strains of the system. So, and what we will do is use an elastic law, so sigma is equal to E epsilon, so E is the Young's modulus. And that will give us a 10th equation, so we'll have 10 equations and 10 unknowns in the system. And note, because of our kinematic assumption that says that the strains are linear on the cross-section, the stresses will be linear on the cross-section as long as we have a single homogeneous material, so just one value v. If we have a composite cross-section, then the stresses won't necessarily be linear on the cross-section, or if we have other types of constitutive laws, we would have nonlinear variation of stresses on the cross-section. But for most of the problems that we'll do, we'll assume elastic homogeneous materials, and so we'll have this linear bending stress distribution on the cross-section. Now let's just go back and talk about this issue of the location of the neutral axis. The neutral axis is the center of rotation for the cross-sections, and we have to determine that to be able to really do any analysis. So, and the way we actually determine that is by using the fact that the force on the cross-section is 0 in most cases. We can also do this with r equal a non-zero value, but what's important is that r is equal to some constant, and that allows us to determine the actual location of the center of rotations. And the reason for that is, consider the fact that r is equal to the integral of the bending stress over the cross-section, and the bending stress is just equal to minus e kappa y. And so I know that this integral of these quantities has to equal 0 in the standard case here. And what that means is that I basically have to place my coordinate origin on the cross-section so that integral comes out to be 0. And that allows me then to find this neutral axis or center of rotation. So let's go ahead and look at a beam. Let's suppose it has a triangular cross-section. And what I'd like to do is figure out where to place the coordinate system. And so I'm going to call that YNA, and I'm going to measure that up from the bottom of the beam. So if I can determine YNA, that tells me where to place the coordinate frame. And I'll introduce a coordinate from the bottom of the beam. I'll call that YB, and we'll use that to transform my integral expression here. So I have r equals 0, and I need the integral of the cross-sectional area, and I'm going to take that integral with respect to dyb dz here. So instead of integrating with respect to y, I'll integrate with respect to yb. But yb is related to y by the parameter yana, which is my unknown that I'm trying to determine. So I'll replace y by yb minus yana. Yana is my unknown here, and I'm going to integrate over the triangle here. Okay, so I can rearrange this equation. Yana is just a number, and so I get an explicit formula that tells me what yana is. So that's where the origin of the coordinate system goes relative to the bottom of the beam. So it's the integral of e yb integrated with respect to dyb dz divided by the integral of e dyb dz. Now, one important observation here is that if e is a constant, I can cancel it from the top and bottom here in the expression for yana, and that will leave me with the expression for yana, which is just simply the centroidal formula here. So the coordinate frame goes at the centroid of the cross-section if you have a homogeneous value for e on the cross-section. So that kind of simplifies things for a lot of problems. So for instance, if you think back to some of the examples we had, where for instance we had square cross-sections or rectangular cross-sections, I place the coordinate frame right in the center of the cross-section there, and so that's the centroidal location of a rectangle there. And for any other cross-section, if you had a circle, for instance, it would also go right in the center. So in most cases, the cross-section goes at the center. But if you have a cross-section that is a bit more complicated, suppose you had a T-section, then the centroid doesn't sit right at the center of the cross-section. It's going to sit at some kind of offset location here. But remember, one of the main results that we had from before when we were looking at statics and calculated centroids is centroids always sit on lines of symmetry. So if you can identify two lines of symmetry on a cross-section, you always know where the centroid is. So if you had an I-beam, perfectly symmetric dimensions here, then you have a vertical line of symmetry and you have a horizontal line of symmetry. So you know the centroid lives right in the center of the cross-section. So for the E equals a constant case, determining the location of the neutral axis tends to be relatively straightforward. But if you have a composite material, then you have to do the integral here in the general formula for the location of the neutral axis. Or if you have a cross-section that doesn't have two lines of symmetry, like the T cross-section here, then you also have to do the integrals to determine the location of the centroid.